Good morning. Myself Dr. Palash, Associate Professor, Department of Chemistry, Semester of Science and Technology. Today, I'll be talking about aromatic hydrocarbons. I'll touch upon concept of aromaticity, Huckel's rule, aromatic characters of arenes, cyclic carbocations, carbanions, heterocyclic compounds, electrophilic aromatic substitution reactions, and mechanism and what is the effect of functional groups in electrophilic substitution reactions. So before starting, let me talk about, is it really necessary to study aromatic compounds? Yes, because we encounter them every single day. You know about petrol, diesel, kerosene, all are containing aromatic hydrocarbons, benzene, toluene, xylene, even that most of the medicines, paracetamol, aspirin, they are all are aromatic hydrocarbons. Starting from that DNA bases, adenine, guanine, cytosine, thymine, uracil, all are related to aromatic hydrocarbons. Plus aromatic amino acids, histidine, then we have tyrosine, phenylalanine, that have also contains the aromatic amino acids. So except that lots of compounds are there containing the aromatic compounds, and that's what that aroma comes from. So aromatic compounds every day we use, and it is essential in industry. About 35 million tons of aromatic compounds are produced in the world, and needless to say, they are very vital to us. So if we consider the resonance energy of 1,3-cyclohexadiene, that is 2 kilocalorie per mole. So one double bond is there, and if you do the hydrogenation, you will get cyclohexane, and that hydrogen energy is 28.6. And when you have the double one, two double bonds, you see that energy close to double, but still 2 kilocalorie per mole less, because you see 28.6 into 2, 57.2, so that's still 2 kilocalorie per mole. So that's why it is telling that resonance energy is 2. But when we have 1,3-cyclohexatriene 135 or benzene, you need only 49.8 kilocalorie per mole. That means expected is 28.6 into 3, but only required 49.8. That means the difference is 36 kilocalorie per mole. That is the energy. It's already there in the system. So you need only 49.8. So that's what it is called, that resonance energy. So you can see that from these diagrams, heat of generate hydrogenations for benzene is much lower compared to your cyclohexadiene. So that indicates that benzene having the highest resonance energy compared to cyclohexadiene or cyclohexane. So from the beginning, people are very much interested what is the structure of benzene, and that 1860 onwards, valence bond theory suggests that there are four bonds will be there, double bonds will be there to carbons, because if you see the non-bond equivalence in BE, it will be 6 plus 1 minus 6 by 2, so that's say around 4. So from then four many structures are proposed, and finally in 1865 Kekulé proposed that it's a cyclic structure, so benzene with three alternate double bonds. So it's look like he has inspired by serpent eating its own tail. So benzene having three double bonds, that will be also alternate double bonds. But the question is whether Kekulé was getting confused why this disubstituted benzenes it has one isomer less, because you see we can make 1 2 1 6 1 3 and 1 4, and although every time people used to extract it or synthesize only the three isomers, why not four? And from there, he has proposed that actually 1 2 and 1 6 they are equivalent, and if it is isomers even, they are interconvertible very rapidly, and that's why it is very difficult to separate. Then finally, in 1928, Kathleen Lonsdale, he has shown the crystal structure of benzene, and he has shown that all the 6 carbon bond length in hexamethyl benzene are equivalent. In fact, later she has determined the crystal structure of benzene where the bond distance is 1.4 angstrom and all the bonds are equivalent. So basically 1, 2, 3, 4, 4, 5, 5, 6, all bonds are equivalent. Okay, and hybrid of these two bonds can be drawn as a ring structure. That means all the bonds are equivalent. Now, if we consider about this 1, 2 bond, and these are actually equivalent. 1, 2 and 1, 6 are they are equivalent, and that's why it is called that dichloro orthodichlorobenzene. Both are same. Now, benzene undergoes substitution reaction, not the addition reaction. Why? Because of the resonance energy. Benzene it can go for substitution reactions of chlorine and ferric chloride. You can get the chlorine substitution. But when cyclohexene reacts with chlorine, it will give that addition product. Why? Because benzene it's a highly aromatic substance. It's highly stable. If it go for addition reaction, it will lose its aromaticity. Later we'll see that how aromaticity maintain its stability. So the benzene does not favor addition reaction because of losing aromaticity. So we are talking about aromaticity. So that indicates that it should have extremely large resonance energy, delocalized pi electron system, and undergoes substitution reactions than addition reaction. And that's what aromaticity actually is not unique to the benzene. All types of molecules having that aromaticity. For example, with multiple rings, polyaromatic hydrocarbons, naphthalene, anthracene, then ring sizes other than 6, 5-member ring, 7-member ring, then heterocyclic compounds, uh, even that the cyclic ring with the positive charge or cyclic ring with the negative charge also aromatic. You can have these examples where naphthalene, furan, indole, pyridine, triiodopylium, cyclopentadiene. So all are aromatic compound except this cyclooctatetraene. You see, this is not a non-aromatic. So what the characteristics to make that these molecules is aromatic? So that is the Huckel's rules theory that tells that molecules has to be cyclic, conjugation, 4 plus 2 pi electron system, and sp2 hybridized nanostructures. And that's why benzene is cyclic aromatic, but this is not, this is acyclic. So whenever cyclic ring is there, possibility of aromatic character. So, but in this case, cyclic aromatic, this is acyclic non-aromatic. But even though it is cyclic rings, where they are non-aromatic because they have to follow other principles. Because in this case, all are not aromatic or conjugated not there. Conjugation two must be conjugated system. You can see this proline is conjugated, but this is methyl proline is not a conjugated system. Similarly, cyclopentadienyl carbonyl is a conjugation conjugated, but this is not methyl cyclopentadienyl. Or phenol is aromatic, but its phytoform is non-aromatic system. So in this way, benzene is a aromatic system because it follows Huckel's rule of aromaticity, cyclic conjugate system, 6 pi electron system. But here, cyclooctatetraene follows 8 pi electron system. But although other characteristics are followed, so that's why they are non-aromatic. Now rule number 4 is it should have 4 plus 2 pi electron system. So benzene having 6 pi electron system, this is also 6 pi. This is a 4 pi electron system. This is a positive plus 2 pi electron system. So it has to follow 4n plus 2 pi electron system where n can be 0 or n can be 2. So you can see this is having 10 pi electron system. This is having 6 pi. This is having 10 pi electron system. So that shows that all the three characteristics compound has to be followed so that they can be called aromatic. Now, how many pi electrons are there in this? Because here pi electrons are very important. So why a compound can be called aromatic, or whether we should consider the lone pair of electrons to be considered as a pi electron system or not. So, for example, benzene with the negative charge, pyridine with one lone pair, furan with two lone pair, pyrrole with one lone pair, and pi. This is your pi pyrazine, right? Pi pyrazine is a Okay, whatever it is. So basically, pyrazole kind of molecules, it has a two lone pairs is there. So what is the condition, especially when we have lone pair of electrons, whether they can be considered, need to consider as a pi electrons, or we should not consider. So, for example, when you talk about benzene ring, it's a 6 pi electron system and it's a perpendicular to the orbitals. Okay. So, whenever you have the negative charge on the benzene ring, so this is a plane. This on the plane, this negative charge is there. So perpendicular to the p orbital system. That's why no need to consider. Whereas in case of pyridine molecules, this is also perpendicular to the plane pi orbital. That's why no need to consider. So in that case, both will be aromatic. But when you consider cyclopentadienyl carbocation as anion, so you can see that pi orbital is perpendicular to the sorry, parallel to the p orbitals. Even in chiral case also it is similar. So we need to consider this lone pair of electrons to be as a pi electron count. In case of furan, you can see that there are two lone pair of electron is there. One is parallel, another is perpendicular. So that means one pair of electrons need to consider. And in case of imidazole, okay, this is imidazole, one pair of electrons need to be considered parallel to the p orbital system, whereas this one we need to consider. So here one good example I am giving, even though there are 10 pi electron system, but because of the hydrogens repulsion, so it cannot be planar. Whereas in this case, that repulsion is not there, that's why it's a aromatic characters, even though it has 4n plus 2 pi electron and cyclic ring. This is the example of 10 annulate system. So structure of benzene, you can see that in benzene is a flat structure, planar, and pi electrons are perpendicular to the orbitals, and that's why that benzenes are also called can be drawn like this. So it can be either this bond or this bond. So all are equivalent structures, and all the carbon bond distance is 1.4 angstrom. Okay, it's not a single bond distances or down bond distance. It's the intermediate. And structure of naphthalenes, you can see that it's a two aromatic rings are fused to each other. So this is also that similar to that benzene ring, and it has a 10 pi electrons and it's aromatic. So here also similar to benzene, naphthalene ring is a aromatic and it's a conjugated system, 10 pi electron system. Let's come to the cyclopentadienyl system. When a proton is taken out, it is a cyclopentadiene anion system, and you can see that this is a conjugated system. So when it has a conjugated system, it will be a planar structures and 4n plus 2 pi electron system, and that's why it's an aromatic system. Now, what is homoaromaticity? Homoaromaticity is that if a stabilized cyclic conjugated system can be formed by bypassing one saturated hydrocarbons like this one, that leads to the homoaromaticity. For example, cyclooctatane when treated with acid, it will form cyclopropylium homopropylium ion. So basically, that it forms a seven-membered carbocation system and excluding this sp3 hybridized. So this kind of system can be called homoaromatic. So benzene and benzene carbanion both are aromatic compound because its negative charge it is a parallel perpendicular to the p orbital, so no need to consider. Again, cyclopentadienyl cation and cation, and it's a 4 pi electron system, but it's not aromatic. Whereas pyrrole, because the lone pair need to consider because it's a parallel to the p orbital system, so that can be called the aromatic system. But pyrrole conjugate acids, because the lone pair ability is not there for pi electron system, so this cannot be aromatic. And pyridine system, because the lone pair no need to consider because it is perpendicular to the p orbital system, so that's why it's a aromatic system, 6 pi electron system. Similarly, thiophene, one lone pair need to be used, and cyclobutene butadiene, it's a 4 pi electron system, that's a non-aromatic system. Or naphthalene is aromatic, or cyclobutadiene dianion. So in that case, need to consider the total 6 pi electrons, so it's an aromatic system. Pyroxenium ions. So where it has a 6 pi electron system and it's a positive charge is there, so no need to consider the lone pair, so it can be aromatic character. Or indoors. Indoors there are 8 pi electrons and to one lone pair need to consider, so it will be aromatic character. If you consider azulene system say it has a, if you consider about the tropylium kind of cations and the cyclopentadiene anion, then we can have that to 10 pi electron system, so it can be aromatic character. Now let's talk about aromatic hydrocarbons. So benzene, when you go for electrophilic substitution reactions, it will give substituted aromatic product, and because through substitution reaction it does not lose its aromatic character, so rather it will not go for addition reactions, because in that case it will lose its aromaticity. So basically when you go for halogenation reaction, so you need a Lewis acid, otherwise this reaction will not happen. So Lewis acid acts as a catalyst, so for example boron trifluoride, ferric chloride, aluminum chloride can be used in. So in this case, suppose you want to have benzene to chlorobenzene you want to prepare, so you can have Lewis acid with the chlorine. Now, what is the use of Lewis acid? Basically, it will be helpful to make that chlorine ion cation. So basically, chlorine and aluminum chloride, it will form Cl plus and AlCl4 minus, and that is Cl3 Cl plus. It will react with the benzene, and it will form that electrophilic substitution reaction. So similarly, all these reaction, chlorination, bromination, nitration, sulfonation, alkylation, acylation, all this reaction is possible. So basically here we need to consider about the electrophilic substitution reaction. In case of electrophile, it will be Cl plus. In this case, bromine plus, in the NO2 plus, SO3, R alkyl and RCO plus. So for example, in case of nitration reactions, so you will be getting NO2 plus and nitro will be substituted. In case of sulfonation reaction, SO3 will be formed from the sulfuric acid. So there are three stages of electrophilic aromatic substitution reaction. First of all, you need to prepare the electrophile. Electrophile has to attack to the aromatic ring, and third one is the deprotonation by the conjugate base. So for example, nitration and nitration reaction where nitric sulfur acid is required, will be getting nitro atom, and then nitro will react with benzene. It will form this sigma complex and say highly unstable, and it will be immediately converted to the nitro product, nitro substitute benzene, because this conjugate base will take this proton and it will regain its aromaticity. Similarly, in case of sulfur trioxide will be little bit sulfur trioxide will be there in giving sulfuric acid, and that will react with sulfuric acid will form SO3H plus. Then benzene react with this cation, and it will form this sigma complex, and finally this conjugate base will take this proton and it will form benzene sulfuric acid. That's all. So loss of SO3H. And field of acylation or alkylation reaction to benzene, when it reacts with alkyl halides, it will form that alkyl substituted benzene. Okay, and when it will form the acyl halides, it will form acyl substituted benzenes. So both cases similar to a field of alkylation reaction, you need alkyl halides. So basically halogenation reaction. So similar to halogenation reaction, alkyl halides will need. So for example, benzene R halide Lewis acid, so you can get that um, R substituted benzene. Similarly, you can have Lewis acid, TiCl4, zirconium chloride, ferric chloride, also you can use it. So if you want to prepare ethyl benzene, you can use ethyl chloride and aluminum chloride, so you can get that ethyl benzene. So how to prepare this electrophile? So basically alkyl halide you need to take which one you want to substitute, then react with aluminum chloride, you will be getting that cation and aluminum chloride anion, and then uh, it will react with the carbocations. So benzene reacts with carbocation, it will form this sigma complex, and then AlCl minus will take this proton and it will form that isopropyl benzene or cumin. But problem is that when you have longer chain alkyl halides, so in that case you will be getting isopropyl benzene, not that propyl benzene. Why? Because in this case, once it is formed the carbocation, so there will be primary carbocation will be converted to the secondary carbocation, and that's why because of the stability of the carbocation, now secondary carbocation react with the benzene and it will form this cumin structures. So that's the problem with the isomerization in case of a longer chained aliphatic halide in case of Trelkov alkylation reaction. But anyway, this problem can be solved using Trelkov acylation reaction. So suppose you want to prepare that acyl CH3COCl, you can have that COCH3 group. So CH3COCl, aluminum chloride, you can get that benzene substituted COCH3. Now, when you are treating with CH3COCl aluminum chloride, you will be getting the CH3CO plus, and this will be reacted with the benzene. You can get that acyl product. Now, if you want to prepare in-propyl benzene, what you have to do? You have to take that ethyl CH3CH2COCl, react with aluminum chloride. You can get this kind of acyl product, and then you have to do the Clemenson reduction, zinc marker ACl, so that you can get that in-propyl benzene. So summary halogenation reactions, bromine, chlorination is chlorine, ferric chloride, you will be getting chlorobenzene. If you react with bromine and ApBeR, you can get that bromobenzene. Both cases, first the chloro and bromo cation will form, then it will react with benzene, it will form the sigma complex intermediate, which is unstable, then it will lose the proton and you will get the aromatic compound, and that's why it is showing that chlorine, ferric chloride, it will form that chlorine plus, and then chlorine plus react with benzene, it will form that sigma complex. Then ferric chloride, it will take this chloride, it will take this proton, and you will get that chlorobenzene. Similarly, when you go for the bromination of benzene, so bromine reacts with PbR4, PbR3, it will form the brominium ion, and then brominium ion react with benzene, it will form the sigma complex, and finally you will get the bromobenzene. Even in case of iodination, iodobenzene also it is possible, but this is something oxidation you need to do. Iodine, when it reacts with on oxidation, you will get the iodide plus. Strong oxidant, you have to use nitric acid or sulfuric acid or cupric bromide. So now this iodo complex will form sigma complex. Then base will be conjugate base HSO4 minus will be taken. So that iodobenzene will form. So last part of the topic, let me talk about that activating and deactivating groups in electrophilic aromatic substitution reaction. So basically, when you talk about that electrophilic substitution reaction, suppose benzene, methyl benzene, trifluoromethyl benzene. So you can see the methyl benzene substitution reaction is much faster compared to benzene, and in case of trifluoromethyl benzene, it is slower. Why? Because methyl group is electron donating group or activating group, so that helps faster electrophilic substitution reaction compared to benzene, because benzene does not have any electron donating group. But on the other hand, CF3 is a highly electron withdrawing group, so it will withdraw the electron density, become that less nucleophilic, and as a result, this electrophilic substitution reaction will be slower. And here is the example of activating and deactivating group. Activating group basically hydroxyl group, alkoxy, ethyl, tertiabutyl, amide, amine. Whereas deactivating group means it will withdraw the electron density from the benzene. You can see most of the halogen atoms, acyl, sulfonyl, cyano, nitro, all these are deactivating groups. Now, why alkyl groups are generally electron donating group? Because alkyl groups are having the inductive effect, okay, electron rich species. So they will be push the electron density towards the benzene ring, and that's why benzene is highly active. Whereas electron withdrawing groups, basically they will withdraw electron density from the benzene ring, and that's why they become less nucleophile, and in that case it cannot accept the carbocation or electrophiles from the other systems. So basically activating groups are electron donating groups and deactivating groups are electron withdrawing groups. So sometimes we have seen that pi donors and pi acceptors are also important. So for example, what do you think? Which group will increase or decrease the rate of nitration? Of course, it will increase because it has a resonance character. Which group, because of its low pair availability, it will push the electron density in the ortho and para position, and because of that, you will get the substituted reactions in the ortho para position. And that's why you can see that oxygen and nitrogen functional groups with lone pairs are highly activating. You can see hydroxyl, ether, O-acetyl, amine, N-acetyl group. So they are electron donating group or activating group. Whereas when you have the pi, so you can see here why their sigma acceptors qualities are outweighed by the pi donation because the lone pair ability, and it will push the electron density towards the benzene ring, and you will see the negative charge will be formed in the ortho and para position. And why halogens are deactivating group? Because halogens are electron withdrawing group. Okay, so it will withdraw electron density towards itself. So they are sigma acceptor. Okay, so as a result, that it will withdraw electron density and it will not allow benzene ring to be good nucleophile to accept the electrophile. So pi acceptor groups are strongly deactivating, for example, nitro, sulfonyl group, carbonyl group, cyano group. So these are electron withdrawing groups. So the rate of electrophilic aromatic substitution reactions are dramatically lower when any of the functional groups are substituted for hydrogen, and each of these groups can act as a pi acceptor. So you can see that there will be positive charge will be creating in the ortho and para position. So as a result, in that position, the nucleophile, electrophile cannot be attracted because it is already electron release substances. So this here we are summarizing that activating group and deactivating group. Activating group basically alkoxide, hydroxy, alkoxy, then methyl, ethyl, alkane, tertiary ester, amide, amine. So you can see that from here to this side, strongly activating group is there. Even the negative charge, if it is known variability is there, then it is a highly activating group. Whereas when we have the deactivating group, so basically positive charge or high strong electron withdrawing groups are part of your electron strongly deactivating group because it will withdraw electron density from the benzene ring. So as a result, it becomes benzene becomes that less nucleophilic and it will not accept the electrophile. So in that case, actually, when you have deactivating group, in that case, nucleophilic substitution reaction will be favored. Uh, Whereas in case of activating group, electrophilic substitution reaction. Okay, so thank you.